Hi, I'm Dennis di Cicco, Senior Editor of Sky and Telescope magazine here at the 2011 Advanced Imaging Conference. And now I'm talking with Rick Hedrick, President of PlaneWave Instruments. PlaneWave is a relatively new name in telescopes, but they've started out with digital imaging in mind for all of their equipment. And I know they've got some very new and interesting equipment here to look at. So Rick, give me a little overview of what we've got right here.
Okay, yeah, I'll show you what we have here at AIC. Right here we have our Ascension 200 mount, German equatorial mount. We have our CDK 17. Okay, and over here we have the CDK 20. This is actually the first product that we offered at PlaneWave. This is an F6.8.
Okay.
And then we have over here, this is the second product we offered at PlaneWave, and this is the 12.5. This one is F8. All our telescopes are F6.8, except this one's is F8.
All right. Now, one of the things we should mention, this is tell me a little bit about the optical design. It's a CDK.
Okay, yeah, so we call it the CDK. That stands for corrected Dow-Kirkham. It's a Dow-Kirkham in the sense that it's got an elliptical primary and a spherical secondary, but we add a lens group right before the focus, and we change the shape of the primary mirror. It's still an ellipse, but it's a different SC constant. Okay, it's a different amount of correction on it, different figure on it. And so we call it a corrected Dow-Kirkham. Probably a more accurate name would be like a modified corrected Dow-Kirkham, but that's getting a little much.
So your secondary mirrors are spherical?
Correct. So the advantage of a spherical secondary mirror is that the alignment is a lot more forgiving. If you have a secondary mirror that has
a complex surface
on it, right? Then it has to be centered really, really accurately to get the performance out of the telescope. A spherical secondary is very forgiving. It has no actual optical axis,
so it's just
you could be off by a couple millimeters, and you would never know this difference once you collimate it.
All right.
So it's very forgiving. And the other advantage to the CDK is that it has a big flat field. So we get pinpoint stars from the center all the way out to the edges of the field. All the stars look the same.
So will all of your telescopes cover the largest chips that are out there today?
Yeah, we cover a 52 millimeter field, and in fact, even our bigger telescopes cover 70 millimeter fields.
Really?
So the big chips right now are a 52 millimeter field.
Yeah.
But there are bigger chips coming out, so we're preparing for that too.
All right. But there's no chip big enough right now that you can't cover with your scopes.
That's true.
Pinpoint stars.
Yes.
Excellent. So would you like to show me a few of the features that you've got here on the 17-inch in your new mount?
Yeah, sure. So as I said before, this is the A200 mount. Some of the features of this mount is it can carry a 275-pound payload, which it can carry our 24.
Really?
Yeah. Now 24, I would caution that it works great in observatory. In wind, I wouldn't use this mount for the 24. So if you have a roll-off observatory, I wouldn't use that. It covers our 20 very easily and our 17 very easily. Yep. It has through-the-mount cabling. So as you can see here, so when you have a telescope with cameras and everything on it, there's tons of cables. So we run through this. You can run underneath this dovetail all the way down through the mount, out through this hole, and then down through the hole that goes down the center, the RA axis. And you can run an extension cord, you can run USB cables, whatever cables you happen to need for your setup. So it's very easy. It's a big 2-inch opening that goes all the way through the entire mount, so you won't get cables wrapped.
Cables are snagging on stuff when you're slewing around. That's nice.
Yeah, so everything can run through there.
All right, now you were telling me earlier that these are the mounts that have high precision encoders?
Yeah, so in addition to having a servo motor with encoders on the motor, we also have integrated on each axis is a high resolution encoder. So they each have, I think on this mount is 14 million ticks per axis. And you have, that is the thing that's governing the tracking of the mount. And we use it for modeling, and we use it for correcting any mechanical errors in the drive system. So we get about 0.1 arc seconds per tick on that encoder, and our tracking accuracy is about between 0.15 and 0.2 arc seconds.
Wow.
RMS error for the whole tracking.
Okay, and when the modeling, you're referring to the ability to point accurately at any coordinate that you put in?
Yeah, so with this mount, we have software that allows you to create mount models, and so you might take 40, 50 stars and create a mount model. So this corrects for all the mechanical flexures in the optical system and in the mount. And using these encoders gives you really accurate mount models. We get mount models, all the time, less than 10 arc seconds.
Tell me a little bit about your focuser system here. This looks new.
Yeah, so this is a new product. This is a heavy-duty focuser with a rotator integrated into it.
All one system.
All one system, and as I said before, that's to save valuable back focus on these telescopes.
All right, so will the rotator go a full 360?
Yeah, it goes just a little over 360. There is a mechanical stop, so in real practice, if something were to happen wrong, you can't wrap all your cables and rip all your equipment apart.
Okay, and you're using the rotator on this telescope so that if you've got an off-axis guiding system, you can actually turn it and select the guide star
Yes,
you
for
want.
framing shots and for finding guide stars.
Right.
For this system, we also use it's also used as a derotator for an Altaz telescope.
Okay, so that you can image in long exposure imaging in an Altaz mode.
Right, right.
All right. Now the thing is, that's heavy duty. How much weight can you put on the back of this thing?
We'd say 40 pounds.
All right.
It can actually lift 200 pounds. Okay. I've actually stood on it and had it lift me up. Obviously, lifting power isn't the issue. It's flexure. Flexure is the big issue.
I can add a little editorial comment here. I had the pleasure of reviewing one of your telescopes a year ago, the 12-inch model, and I said that I had never had a camera coupling system as rigid and strong as the one that was built into this. It really was a superb system.
Thank you. We really try to have, we call this the secure fit.
Yep.
Spacers, CCD spacers, and we do that, everything bolts on. It takes a little bit longer to put them on, but we have heavy, very expensive CCD cameras, and you just can't have anything move. Yeah. So secure fit is the only way to go, in our opinion.
And I'm assuming that all of this stuff can be remotely run by computer.
Oh yes, yes.
No question.
In fact, it's really, all our work for the last year has been spent on making everything so it can be remotely controlled.
Well, I tell you, I know where we really want to go here. You've got the big thing at the show that's attracting a lot of attention. I want you to tell me a little bit about this.
Yeah, okay, so this is the CDK 700. It is a 0.7 meter or 28-inch telescope. It's a CDK also, but it's a little bit different in that it has a Naismith focus. So that means the focus comes out the side here, as opposed to going out the back. And the advantage to this, there's several advantages. One is that the eyepiece or camera is always at one height. Another thing is that we're not changing the balance of the telescope by putting heavier and lighter things on here. And the other advantage to a Naismith focus is that if you rotate the tertiary, if we rotate that around, you can point out the other Naismith port. And there you can put an eyepiece. So you can have a camera on this side and an eyepiece on that side, or you can have a spectrograph on that side and a camera on this side. And for universities and such, having the eyepiece at one height is great for wheelchair accessibility.
Oh, really?
Yeah, and it actually, Alan Keller, who did a lot of the design on this, actually found kind of the most popular wheelchair height and set it at that just for...
Actually thinking ahead.
Yeah, thinking ahead.
So here now you've got the heavy-duty focuser rotator here, and you need the rotator in this device because you have to rotate the camera as you're taking your exposures.
Exactly. So this is derotating the sky rotation because we have an Altaz telescope.
Right.
So and you can also frame the shots with the same thing.
All right.
And it's focusing. So
tell me a little bit about the motor drives in this.
Okay, yeah. So I told you about the Naismith focus for the CDK 700. The other neat thing about this is the mount itself. This is sort of a state-of-the-art mount. This is a mount. It's a direct drive motor. So they're big pancake direct drive brushless motors in here.
In other words, no gears.
There's no gears in here at all. That's right. There's just the bearing and the magnetic fields holding this thing in place. And there's one on that axis and one on this axis. You can actually move it, break it free because there's no gears, and it goes right back to the position it was to encoder tick accuracy. So right now it's back and it's tracking again. And you can do the same thing with this axis. Ugh.
Okay, so if the thing were disrupted by wind or something like that, it's going to go back to where it needs to be.
That's right, and it actually does even push against wind. When it sees something push against, it pushes harder against it.
So tell me a little bit about the drives.
Okay, so this telescope does not have any gears in it. It is a direct drive system. There's a direct drive motor on each axis, and as you can see here, this is the azimuth axis. And there's a V groove there, and there's little tiny, ball bearings there. This thing runs, it's a stainless steel V groove. And you can see these black guys here and here. Those are magnets, rare earth magnets. And then here is the top section, and this is these are 24 coils. This whole thing sits on top of that, and the only thing you've got is the bearing surface touching. So there's no gears, no backlash, and
the base of the telescope is basically the motor.
yeah, the whole base of the telescope is the motor, and integrated into that is the encoder. So here we can see the encoder here on the system all put together. And so you've got this motor, you've got the bearing, an encoder, and the magnets all into one motor, one system, and the whole telescope sits on top of that. So zero backlash in the system. It's very responsive. Where gears have little hesitations and backlash and things like that, this instantly responds one way or the other. So it makes for a very stiff, reactive mount.
So where are the controllers for all of this system?
So we have an industrial controller that sits inside of this box that goes on the side of the observatory. And if you look inside, we have all the controllers that are controlling the mount. You've got, here are each axis controller, each motor controller. This talks to the computer over here. We've got a power supply for the control voltage, 24 volts, and we have 12 volts, which goes into the telescope just for all the accessories. So this panel sits on the wall. There's an emergency stop on the front of it here. Emergency stop and on-off switch. It's all industrial grade controllers. Easily replaceable if something went wrong. They're off-the-shelf components.
All right, you want to slip the telescope around so we can just watch it go?
Oh yeah, let's do it.
All right.
Do a jump here in RA, an incremental jump. Here we go.
Totally silent.
Yeah, totally. And I'll sloop back here in a moment. But again, if I just bump it, push it off, it goes right back to the exact point it was at. And then we'll just sloop it back to the same point. It's really a fun thing to see. And now on top of that, Dennis, we have a chart here that shows our tracking error. And here we can see the RMS azimuth error and the RMS altitude error. And this is in arc seconds, so it's 0.05. It's an encoder tick sort of accuracy. The encoder ticks, and here we're seeing just the noise in the encoder ticks.
So if I go give the telescope
so
a
give it a
bump
bump.
here.
Give it a big bump.
All right.
The scale changes on here, and it shows the error. In fact, even if you stomp your foot, you can see, since this floor, now you can see the RMS has come down, but now the scale's changing and it'll start to show more error, more noise here in the measurement.
That's accurate. Now you can, obviously under computer control, you can track virtually anything. I mean, you can track satellites if you've got the right coordinates.
Sure, yes.
Any moving object, and you can move very fast.
We can move very fast. Right now we set it to 10, we can move 15, there we just bumped it. We move 15, we can move 20 degrees per second. We kind of set it to 10 because it's a big telescope, it's something moving that fast. Yeah. You know, it doesn't really need to move much faster than that for most applications. So, and it's silent, so it can bang in the head before you even know it's coming.
At you, yeah.
It's like the new electric cars that are all silent.
So looking at the computer screen here reminds me, you've got a new focusing system. You want to tell me a little bit about how that works?
Right, yes. So we have a focusing system that's unique in the sense that what we use is we take the whole image. We take several images and we analyze the whole picture, the whole CCD chip,
so
of the multiple stars. So on each image, so what we do is we take 4, 5, 6 images going through focus.
Moving the camera each time between the exposures.
Yes, and then we analyze the whole image and we calculate the RMS spot size of all the stars in the image rather than just one star, which most focusing routines do. So if you have a slightly curved field, or if you have a slightly tilted field, or if you have any imperfection, and not only that, just the noise in one little piece of the sky, we have a lot better statistical averaging on focusing. So we can focus on the whole image, or we can focus on the center quarter of the image.
All right,
and it's a great little automated tool that we use all the time. And I think right now it will only be available on our telescopes, but maybe in the future we'll have it ASCOM compatible and maybe be available for some other focusers too.
And that's really impressive because it gives you the ability to really just get the best overall focus for the whole thing, or if you're interested in the very center, the best overall focus for the center.
Right, exactly.
Sort of a modern adaptation of what some of the new DSLR cameras are doing with their multi-point focusing systems.
Well, the reason we developed this, one of the reasons is that we wanted to analyze tilt of image plane tilt. And so on the screen, when we do like a V curve and everything, but it also shows you the image plane tilt of your shot. So, you know, with these big CCD chips, we're also sensitive to any image plane tilt. If you have a little bit of image plane tilt, that means you're in focus in the center, but not in focus in one corner, not in focus in the other corner. So this way you can figure out if there is image plane tilt and then do something about it. You can shim your camera if you need to. So it's a really great, that tool is what got us to develop this software. It was really for that in the beginning.
All right, amazing stuff. Anything else you want to show me?
Well, actually there's one fun thing that we've got that we're working on. Here I have an iPod Touch, and but it also works with an iPhone. And this is a little web app. It's not an iPhone app, but it's a little web app that's talking to our computer, and I can talk to the telescope and slew it. Here's making a 30-degree right ascension movement. There it goes. And I can move it back. I can control the focuser with this. You know, it's just a fun thing that we've been playing with that we realized we could do. And
why not? One more reason that you have to have an
That's
iPhone,
right. Yeah. Yeah, we jumped on the bandwagon. So.
Very good. Well, listen, thank you very much for showing me everything you've got here. It's exciting stuff. It's nice to see all these telescopes at AIC. I really wish you a lot of luck.
Yeah, thank you very much. It's a real pleasure for us to be here at this show. This AIC show has, you know, incredible attendees, and we like to bring a lot of equipment to show to them.
Well, this is
and
your
it's
crowd.
a great audience. Yeah, it's really a great show, and we're really happy to be here.
High-end imaging people.
Absolutely.
Right,
thank you very much.
You're welcome. I'm Dennis di Cicco for Sky and Telescope Magazine here at 2011 AIC in Santa Clara, California.